Hey guys, and welcome back to another video in my series of videos that I'm doing on electromagnetism. In the last video we covered the basics of electrostatics, including things like the electric field and the electric potential. In this video we're going to kind of take these ideas a little bit further, and we're going to derive Gauss's law, which is a very important law in the theory of electromagnetism, and it's actually one of Maxwell's 4 equations, so it's a pretty fundamental cornerstone. So we're going to talk about what it is and also how to apply it. So it's going to be a couple of examples on how to apply Gauss's law in various different geometries and coordinate systems. So yeah, let's get right to it. So I want to start this video off by considering a sphere. I'm going to consider a sphere. Now, initially this sphere, well, firstly it's going to be made out of metal. So this is going to be a metal sphere. Imagine it's some massive ball of like iron or lead or something like that. So let's take this metal sphere. Now, what do we know about metals? Well, we know that metals conduct electricity. But what does that actually mean? Well, we know that the structure of a metal, it includes a lattice of ions right here, and these are positively charged ions, and around these ions is kind of like a sea of delocalized electrons. Now, depending on the metal, each atom will contribute a certain number of electrons. That will change depending on the metal, and obviously that's going to change the conductivity of the metal. But the question is, what happens when we apply an electric field to this metal? Well, say we apply an electric field here, so the positive end will be here and the negative end will be here. So that means the electric field lines will run the other way around. The electric field lines will run in that direction right here. Well, what's going to happen? Well, we see all these little electrons whizzing around right here. Well, all the electrons which are negatively charged, they're all going to move to the positive terminal, aren't they? They're all going to move towards the positive end. So if I redraw this, you're going to have all the ions are kind of fixed where they are. They're not going to move because they're kind of part of the structure, and they're also much heavier than the electrons. But the electrons, there's basically no mass, and so they're all going to move to the positive end of the terminal right here. So here's the positive end, here's the negative end, and what you're going to have is there's going to be a net surplus of electrons on this side, and a net deficit of electrons in this side of the metal. So basically the electrons are going to move until there is no net force. They're going to reach steady state or equilibrium. They're going to move until they kind of hit this configuration right here. So what's the consequence of that? Well, the consequence is that inside this sphere right here, there is in fact no electric field. The electric field completely cancels itself out. The reason why that's the case is because these electrons right here, they move in such a way as to completely counteract any electric field that would have been there. So say you have like our charged ball right here, our charged sphere right here, and it's just completely neutral. You've got your lattice of metal ions, and then you've got your sea of delocalized electrons. What happens, say, if we're going to put a positive charge right here? Well, this positive charge is going to affect all of these electrons right here. All these electrons are going to move, and they're going to move in such a way so as to completely cancel out any electric field produced by this positive charge right here. So if you take anywhere inside the sphere, then there's going to be no electric field, because the electric field generated by this positive charge is going to be completely cancelled out by the electric field produced by all of these negative charges right there. So this is a case for metals in particular. Now later on we're going to have a look at dielectrics, and dielectrics are kind of like somewhere in between a vacuum and a metal. So basically there will be kind of like a response from inducing like a charge. However, it won't be a response so as to completely cancel out the electric field. But the take-home message from this is that inside a metal conductor, inside any sort of conducting medium, then the electric field is zero. And of course, if the electric field is zero, that basically means that the electric potential inside V is just a constant value. So that means the voltage of this conductor is exactly the same throughout the entire cross-section of the sphere. So now we're going to have a look at Gauss's law. Now, in order to understand Gauss's law, we first need to quickly revisit the concept of vector flux. Now, I did cover this in my maths video, but I will go through it again briefly. So say you have some electric field right here. So say for the purposes of this example, it's going to be an electric field which is pointing in the same direction. So these electric field lines are parallel. So this is not a radial field which would be produced by a point charge. This is a parallel electric field. And say we have some kind of surface here, right here. So here's our surface. I'm going to sort of draw it in 3 dimensions, just so it's kind of clear. Well, obviously how much flux you get from this is going to be dependent on both the magnitude of this vector field right here that's incident on this plane, but not only that, the direction as well. So obviously if you have like your plane right here and you have your field coming in completely perpendicularly to the plane, or completely normally, then you're going to get the maximum amount of flux right here. But obviously if you have a case where here's your plane of incidence, and in this case you're going to have the things coming in right here, you're going to have it coming in at, say, like an angle, then you're going to have a reduced amount of flux right here, because of course, you know, even though this is the same intensity, it's still going to be a different direction, and so therefore the received amount of flux is going to be much, much less. And the way we quantify it is, of course, with the dot product. So say we have our vector field A, this is just some arbitrary vector field I've dreamt up on the spot, then the flux, which I'm going to call phi, is equal to A multiplied by the dot product of the surface right here, and this is the surface area, S right here. Now, the direction of the surface vector is always in the direction which is normal to the plane. So in this case right here, it will be right here. It will be kind of sticking, you know, perpendicularly outwards. So that would be the direction of S. Now, of course, say we have a vector field A that changes throughout the surface. Well, in that case, you have to do an integration, and therefore you get that the total flux phi coming out through the surface is the integral over the surface of the flux density A, dot producted with each area element right here. So that's kind of like if A kind of depends on sort of whereabouts on the surface you are, then you're going to have to do like an integral in order to get the total flux. So now I just want to consider a single point charge at the origin. So we saw this in the last video. So we have our point charge here, and it's located at the origin of our coordinate system. Now we're going to be using spherical coordinates because, of course, we have a point charge, and we know that for a point charge the electric field lines are going to point radially outwards in every single direction. So for that purpose we're going to be using a spherical coordinate system. Now we know from the last video that the electric field of a point charge is Q over 4 pi epsilon 0, and it's 1 over r squared in the r hat direction. So that is the electric field as a function of distance. Now what I want to do is I'm going to consider a sort of imaginary surface around this point charge. Now it's going to be an imaginary spherical surface, or if you like, you can think of it as sort of like a sphere that's made out of plastic or something, some non-conducting material. But the point is that it kind of encapsulates this charge completely. And it also reflects the same geometry as the electric field lines that emanate from the point charge. So obviously you can see that at any point along this perimeter right here, along the surface, along this kind of shell surface, then the electric field is going to be the same. And that's true for this particular spherical geometry. So you're going to have the charge Q. And let's say we have a little window right here. Let's say we have a little sort of window in our sphere. And this is going to be a surface area element ds. It's going to be a really, really small surface element ds. And say this surface element points normally n hat in the direction of the kind of the shell right here. So normal to the surface at all points throughout the sphere, because of the niceness, if you like, of the spherical geometry. Then if you take any window right here across the surface of this plastic sphere, then it's always going to point sort of away from the point charge. Now what we've kind of done here is we've kind of chosen a surface, this kind of plastic sphere thing that I'm talking about. We've kind of chose this surface to reflect the electric field lines that are coming across from this point charge right here. Now this is a very important choice, and that basically makes all of the maths that follows from here on in really, really simple. So we don't have to worry about norm like dot products and cosines of thetas or anything like that. We've chosen a geometry that works. So ds is always ds in the n hat, which in the spherical coordinate system is ds in the r hat direction. And of course the r hat direction, I said, was the direction of the electric field, always pointing radially outwards. And so we've chosen this surface such that the normal to the surface is always r hat, and that basically makes all the maths really, really nice and simple. So now I want to ask, how do we get the total amount of electric flux coming out through the sphere? Well, just like for this arbitrary case right here that I did with this imaginary vector field A, then we just have to do an integral over the surface of the electric field all across the surface, or with the dot product with the infinitesimal surface element right here. Well, we know what the electric field is. The electric field is Q over 4 pi epsilon 0 1 over r squared in the r hat direction. But what is ds? Well, ds for a sphere, I did cover this in a previous video, but ds for a sphere is r squared sine theta d theta d phi. Now, if this looks really weird to you, then I encourage you to go back and watch my video in which I cover this. Then hopefully that will make a lot more sense. But basically, I'm taking the surface element for a sphere, and I have simply substituted it in, and also I just forgot the r hat right here. So what's going to happen? Well, you can see that these r squared right here, this is the kind of the important bit, the r squares are going to completely cancel right here. So if we simplify this out a little bit, we're going to get Q over 4 pi epsilon 0. That's all just constant, so we don't have to really worry about that. And now we're going to have a double integral. We're now integrating over the polar angles theta and phi. Of course, the electric field does not depend on theta and phi, which is going to make the integration incredibly easy. But yeah, this is what essentially we're doing. So we're now doing sine theta d theta d phi, and of course we have r hat dot r hat, but as we saw in the last video, that just simply turned out to be 1 because of course they're both unit vectors and they're both in the same direction. So r hat dot r hat is 1, and now the integral reduces to all scalar quantities, so we don't have to worry about that. So what happens if we do this integral right here? Well, we're going to get q over 4 pi epsilon 0. We can actually separate this integral out into all the terms with theta in, so sine theta d theta multiplied by the integral over phi right here. So now all we need to do is do these integrals, and the way to do that is we kind of first need to know what the limits are of the integral. Well, theta, this is going to be across the entire spherical surface, so theta is going to run from 0, which is like the north pole, to pi, which is kind of like the south pole right here. So remember, theta was kind of our angle, which kind of swept all the way across right there. It's kind of a bit like latitude if you're on like a globe, whereas phi, which is kind of our longitude angle, runs from 0 to 2 pi. So that kind of runs all the way around the world like that. And so those are going to be our integrals. Now, of course, the phi integral is going to be pretty straightforward, so I'll just do the phi integral first. So you're going to get q over 4 pi epsilon 0, and when we integrate that, we're just going to get phi evaluated from 0 to 2 pi multiplied by the theta integral, which I'll do in a minute, but I'll just do the phi bit first. So that's just simply going to be 2 pi, right? So all you're going to get is 2 pi minus 0, which is just 2 pi. So you're going to get q over 4 pi epsilon 0 multiplied by 2 pi, and that times the rest of it. And so you're going to get, that simplifies to q divided by 2 epsilon naught times this. So now let's actually go and evaluate this thing. So integral of sine theta with respect to theta is of course minus cos theta. So again, minus cos theta evaluated between pi and naught, which is going to be, so here's all our other stuff, which is all constant. You're going to get minus, so cos of pi is minus 1, minus cos of 0, which is just 1. So you're going to get minus 1, which is minus 2, but then that all gets multiplied by minus 1, which makes that 2. So actually this is just going to completely reduce down to q divided by epsilon 0, and that is the electric flux generated by this point charge in this point charge in this kind of spherical geometry. But what did we say the electric flux was? Well, we define the electric flux as the integral of the electric field all over the surface right here. And that right here, I am pleased to say, is Gauss's law. There it is. That is Gauss's law. And that is the first of Maxwell's 4 equations. And it's basically saying that the total flux is simply equal to the charge enclosed by the sphere divided by this epsilon naught, which is the permittivity of free space. So that is how you can get from the electric field to the charge and vice versa. Now this form right here is what's known as the integral form of Gauss's law. Fairly obvious reasons, this because of the integral sign right here. But there's also a differential form of Gauss's law, which is pretty easy to derive if you know the integral form. And I'll show you how to do that exactly. So if you remember in the last video, I defined this concept of charge density rho, which is the charge per unit volume, or if you have a charge that depends on volume, then it's dq by dv right here. So it's the charge divided by volume. Now, if you want to go from the charge density to the charge, then you simply, rather than differentiating, you have to do a volume integral. So we found that the total charge, Q, is the integral over the volume of the charge density all across the entire volume right here. So that is how you get from the charge density to the charge. You simply have to do an integral. Well, let's just go ahead, and what we can do is we can just go and substitute that into Gauss's law. So rather than Q, we're going to put, so we have our 1 over epsilon naught on this hand side, and rather than Q, we're just going to substitute in this integral right here. So it's going to be the integral over the volume of rho, which is the charge density, all across the volume. And that is, of course, equal to the surface integral of the electric field across the surface right here. Now, what we can now do is we can apply the divergence theorem to the right-hand side of the equation. Now, if you remember, the divergence theorem actually converts between volume integrals and surface integrals. And so what we're going to do is we're going to get this integral here on the right-hand side into a volume integral. So how are we going to do that? Well, we know that so I'll write out the divergence theorem. So the surface integral, as long as it's a closed surface, across the surface is equal to the volume, or the divergence of the vector field. So the divergence, which is of E, of the vector field, all integrated across the volume. I derived the divergence theorem in one of my math videos. So this is what we're going to be using, and we're going to substitute this into the relation above. So what we're going to get? Well, we're going to get 1 over epsilon naught rho dv, so the left hand side is still the same. So that's the volume integral, and on the right hand side we're going to get a volume integral, but this time it's going to be of the divergence of E, all integrated across the volume. But as you can see, we have two volume integrals which are essentially over exactly the same volume. But of course the condition right here is that this is a volume which is enclosed by this surface right here. So in order for this to work, it has to be a closed surface, which is a very, very important point. The surface can't be open, it has to completely encapsulate a volume in order for it to work. So, well, what we can do right here is we can simply just, we can see that these are just integrated over the exact same thing. So in fact we can kind of de-integrate them, if you know what I mean. So just take away the integral signs, and then we can get that rho over epsilon 0 is equal to simply the divergence of the electric field right here, and that is Gauss's law in differential form right here. And so all we did was we used the divergence theorem to convert between the surface integral to a volume integral, and then we just simply noticed that the two volume integrals were over the exact same volume, and so all the terms in the integration must be exactly the same. But of course the condition right here is that the surface is closed. The surface must be closed, and it must, and that basically essentially means that it must cover a volume, because of course if you have some kind of open surface right here, well, it's not going to encapsulate any kind of volume, is it? So therefore you're going to have a closed surface in order to encapsulate a volume. So that is the condition, but that is Gauss's law in differential form, and it depends on kind of the question, but sometimes you'll find that Gauss's law in differential form is much easier to work with than Gauss's law in integral form. It just depends on the geometry and how easy it is to take the divergence in certain geometries. And also, I guess it's personal preference whether you prefer doing an integral or taking the divergence, basically. So Yeah. So lastly in this video, I want to do an example of how you can apply Gauss's law in a slightly less straightforward case. So of course the point charge is kind of the easiest example, but of course you're not going to be given a point charge necessarily all the time. And so for this example, I'm going to consider a line charge, kind of a line of charge right here. So this is, imagine it's kind of like a wire or a metal rod that's kind of that's charged, and so this is going to be a positive line charge right here. And I'll just move it down here so we have a bit more room to work with. So the question I want to ask is, what is the electric field and the electric potential of this line charge right here? Well, in order to get the electric field, we can use Gauss's law that we just derived. The nice thing about Gauss's law is that it works for any kind of geometry, provided we have a closed Gaussian surface. So what surface do we choose? That's the big question, because we want to choose a surface such that the normal to the surface is always parallel to the electric field lines. So, well, let's have a look and see what the electric field lines of this surface are going to be. Well, since this is a 3D, this is going to be, of course, in 3D right here. The electric field lines are always going to point away from this line of charge right here. So they're going to point upwards here, but they're also going to point downwards here. So it's not actually going to be a spherically symmetric distribution of charge. It's actually going to have what's called cylindrical symmetry, because of course all of these, if I sort of draw it in 3D, it might be a little bit clearer. So here's our wire, and the electric field lines are all going to point, radially away, but kind of in a all across the entire wire. So as you can see, it kind of has cylindrical symmetry. Kind of the electric field lines resemble the shape of a cylinder, and so it's for that reason that we're going to be using a cylindrical coordinate system, which of course has the coordinates r, theta and z, where r is the distance from this kind of wire, theta is the angle around the wire, so it's the angle in that direction, and z is sort of how far up the wire you are. So that is what we're going to be using. And so what surface are we going to choose to encapsulate this? Well, it's for that reason we're going to choose a cylindrical surface, because the cylindrical surface reflects the symmetry of the electric field lines, and so that's what we're going to be doing right here. So here is our imaginary surface, or our plastic surface if you like. So what's the electric field lines going to be? Well, and I hope you guys can see that any electric field lines which would be going through this surface right here will be completely cancelled out by any electric field lines that are going through this surface right here. And the reason is that all the electric field lines are going to point straight upwards, and so any electric field lines that are going sort of that way are just going to be completely cancelled out. So in fact, there's no point in doing any integration over this surface nor this surface of the cylinder right here. So all we want to do is actually integrate over this bit right here, this kind of cylindrical surface. And so what are we going to do? How are we going to do that? Well, let's write out Gauss's law to start with. So E dot ds equals the charge enclosed divided by the permittivity of free space. So that's Gauss's law in its general form. So first thing we need to really sort out is this kind of charge term right here, because at the moment the charge term isn't really in a kind of thing that we really want. So what we're going to do is we're going to define a quantity called lambda, and lambda is the linear charge density. It's the charge per unit length. So it's going to be dq by dl right here. Or in fact, since this is going to be our z-axis, then it's going to be dq by dz, I think. So So that's the line charge density. It's the charge per unit length. So it's the charge in 1 meter of length, basically. If it's constant. Of course, if it's not constant, then you have to do this kind of thing right here. But in this case, we're going to assume that the charge density, the linear charge density rather, is a constant. And so what are we going to do? Well, we're going to, like we did with the volume charge density, we can kind of turn this equation into on its head and make it into an integral equation, and rearrange it such that the charge is the integral of lambda over z right here. So it's lambda integrated over z. Of course, this is the general case. It turns out that in this example, lambda will be a constant, but if it's not a constant, then you have to use this integral form nonetheless. So I guess I'm kind of showing it for like the more general case. So let's go ahead and substitute this in. So the left hand side is still going to stay the same, E.ds, and then we're going to have our 1 over epsilon naught, and we're going to have the integral of lambda dz right here. So that's all good. Now we need to evaluate the left hand side a little bit more. And to do that, we need to remember what the surface element is for a cylinder, a cylindrical surface right here. Now, the cylindrical surface was kind of the surface of constant radius right here. If you think about like a cylinder, it's kind of the outer kind of rim, rather than like the caps on either end. It's going to be this kind of outer rim. So the radius is going to be constant. So it's not going to depend on r. And if you remember what it was, then ds is equal to r d theta dz right here. So again, that was from my video on different coordinate systems, one of my math videos that I did earlier on. Again, if you haven't seen it, I do encourage you to go and watch it. But yeah, that is what that's what the magnitude of it is. Of course, the direction, what's that going to be? Well, this direction right here is going to be sort of pointing radially outwards at all points, and so it's going to be in the r hat direction right here, which is very handy because of course the electric field is also in the r hat direction. And so because of this surface that we've chosen, we've got a situation in which once again the electric field and the surface normal vector is in the same direction, and so it will simply, the dot product will be 1, so we don't have to worry too much about anything. So let's go ahead and write this in. So we're going to have E, and instead of writing E vector, I'm going to write E scalar multiplied by the unit vector. That's exactly the same thing. I've not changed it at all. I've just written it out in a slightly expanded form. Multiplied by ds, which is r d theta dz in the r hat. And like I said, the two r hats are just going to become 1, so we can ignore them. And we're going to have 1 over epsilon naught on this hand side, multiplied by lambda dz right here. So that's looking good. So as you can see, this integral on the left hand side is only over theta and z. In fact, really it's a double integral, and as is the case with any double integral, we can separate it out. We can also factor out the constants as well. So E is simply a constant. E doesn't depend on theta and z. E only depends on r. So that can come out. The r can also come out. And so therefore we're going to have our first integral, which is d theta, and we're going to have our second integral, which is dz right here. So the right hand side, we're going to have our 1 over epsilon naught multiplied by lambda dz. And now we need some limits. So we now need to decide what kind of thing we're integrating over. Well, if we have a look at this right here, then we can see that the theta bit's going to be quite easy. The theta bit's just simply going to be all around there, right here. and that's going to simply be between 0 to 2 pi. So that's going to be the theta bit. Now for the z integral, we can actually just choose literally anything, to be honest. So it doesn't really matter how far along, because as you guys can probably see, as long as you do the same integral on both sides of the equation, then it's just simply going to cancel out right here, because of course lambda, I said, was a constant, and so therefore when we integrate lambda with respect to z, we're just going to get lambda z, and it's just going to be exactly the same on this side. So I can just kind of invent some arbitrary length L, which are the limits, and of course you guys can probably see that it's just going to completely cancel. In fact, actually it's clearer if I factor lambda out of the integral. Of course you can only do this if lambda is a constant, and then you can just simply see that we have exactly the same thing on the right and left hand side, and so that's just going to completely cancel. And that kind of tells you something quite interesting, actually. It tells you that the electric field does not depend on z at all. It's exactly the same all across z, which basically means that it's got cylindrical symmetry, which is what we thought because it was cylindrically shaped. So let's just finish this up. So we're going to have ER, theta between 0 and 2 pi, so it's 2 pi, and that equals lambda over epsilon naught. So we can simply tidy this up to say that the electric field is lambda over 2 pi epsilon 0 r. But of course the electric field is a vector quantity, so we just need to add a unit vector on the end of this equation, and then we'll have a vector. So 2 pi epsilon 0 r, all multiplied by r hat once again. Now of course this r hat is not the same r hat as the spherical r hat. This r hat is just the one that points radially away from this line right here. So yeah, so that is our electric field as a function of the radial distance r, and it only depends on r. It doesn't depend on theta, and it doesn't depend on z either. So that's kind of what you'd expect. You'd expect the electric field to decrease in strength away from the wire, and you wouldn't expect it to change depending on how far up the wire you are. So yeah, so that's how you'd find the electric field strength of a slightly more complicated geometry. I've actually included a list of examples that you can try to find the electric field strength of. I do encourage you to have a go at these, because you'll probably get a lot of these questions coming up. It's just basically all about looking at the system, deciding which coordinate system to use, deciding what the easiest way is of evaluating the integral. And yeah, sometimes you're going to have some slightly more complicated cases. I will maybe do another video covering a few examples of some more complicated cases. But basically, yeah, that is the general idea of Gauss's law, and that's a simple application of how you can apply Gauss's law. So yeah, so that kind of wraps up our little mini topic, if you like, on electrostatics. In the next video we're going to be starting to look at electric dipoles, so see you guys then.